Now, hydroxide ions actually act as excellent Lewis bases because they can readily donate away an extra pair of electrons. If you imagine what a hydroxide ion looks like, and we're going to show you one in a second, it comes from the loss, and I'm going to oversimplify this a bit, but it comes from the loss of this hydrogen to another water molecule. So that hydrogen leaves and joins another water molecule over here, which will become a hydronium ion. But this oxygen doesn't need any more electrons, just the hydrogen leaves, leaving our OH behind with an oxygen that has 3 pairs of lone electrons. And it can easily give up one of those pairs, donate them to something else, making it a very good Lewis base, a great donator of electrons. So you can see that example if we look here. Why metal hydroxides, another hydroxide can be added into them, making another coordination complex. Again, noting that metal hydroxides can either choose to be an acid and add another OH, or they can be a base, and if you add a bunch of hydronium ions to them, you'll create just the metal ion with waters. So they're that situation where they are ambiturners, as we talked about in class a little bit. They can decide to go either way in the reaction. If we look at a molecular Lewis acid, we'll look at why oxides of nonmetals actually are going to behave as acids. That goes way back to the beginning of class. Most of us got these problems wrong when we had them on our quizzes. Why, when you have SO2 or some sort of nonmetal oxide, or SO, whatever you may have as a nonmetal oxide, why it's going to be able to create an acid, why NO2 can create with water nitric acid.